It's one of those situations where if no one's here, then you just write this all down, but pause it to write it all down and then listen to me talk about it. 1, 2, 3. Okay, now that you've got it written down, perfectly elastic collision, both momentum and kinetic energy are conserved. Because it's one dimension, change left and right to negative and positive. So usually we assume kind of right to the east and so on is positive, west to the left is negative. But there's a couple formulas there to find the final velocity of each one. So there's that. Moving along. There are some special cases. So one, when the objects have the same mass, they exchange velocities as if they pass through each other. And it says when they pass through each other, it's as if their velocities pass through each other. So the final velocity of the item 1 is the negative, so different direction from the initial velocity of it. So it's same velocity, but just turns around, goes the other way. Imagine kind of two pool balls. I think I was thinking of cue ball. Two pool balls come into each other. They hit each other square on. If there's a 100% transfer of energy, nothing is lost in friction or sound, stuff like that. They would hit each other and then just go back the way they came. If one was coming fast, the other one coming slow, they hit. The slow one is now fast, is taken on the velocity of the faster one. The faster one takes on the velocity of the slower one. Hopefully that makes sense. When one object is much heavier and stationary, the lighter object simply reverses its velocity. In physics terms, when they talk about much, that's not like it's not like I'm a lot heavier than Micah, but I'm not much heavier. It would be more like a person running into a car kind of a thing. It's a violent image, not what I meant, but ball against how about that? Basketball against the car. It just comes back. The car's not going to roll away or anything like that. All right. Now, if a spring is involved, let you copy this down. If you have a spring or a bumper on one of the objects, that spring will take on some of that mechanical energy. So you've got your kinetic energy equals kinetic plus the spring. Now x, if x is 0, which means there's no movement, like the spring, at whatever point you kind of look at this, the spring is not engaged, then this whole thing is 0. So it's just kinetic energy equals kinetic energy. If it's compressed at all, that's where some of this energy gets transferred into here. At maximum compression, you can use this equation instead. Cool. Tutorial 1 and 2, questions 1 to 6. I think we'll do some examples here. Oh, excuse me. Set this up. Okay, I'm going to stop screen sharing, which means it should be, yes, my arm. Okay, that looks decent. Maybe let's get a little bit more intimate. Lessen my frame. All right, so page 243, number 1. A ball of mass 80, so mass equals 0.08 kilograms. That's M1. Is moving at 7 meters per second west. So V1 initial equals -7, because 7 west, 7 to the left, so I'm going to call it -7. Undergoes a head-on elastic collision with a stationary ball of mass 60, 0.06. It's stationary, so V2I equals 0. Calculate the velocity of each ball after the collision. All right. So let's go to the formula that we were given. So put it right here. So VF1, or sorry, VF1 equals, write this out, M1 minus M2 over M1 plus M2 times VI1 plus 2 times M2 over M1 plus M2 times VI2. So this equals M1 minus M2, M1, so 0.08 minus 0.06 over 0.08 plus 0.06 times VI1, which is negative 7, plus 2 times M2, so that's 0.12. M1 plus M2 is 0.14, but VI2 is 0, so don't even need that stuff. So we just multiply this through. So it's 0.02 times negative 7, forgot my negative, divided by, put the negative here, negative 0.14, negative 1. Is that right? Did we do it right? We did. Negative 1, which means, so here, equals negative 1 meters per second, which means this is probably a 2 sig fig question. Yes, so it's going to be 1.0 meters per second. That negative means it's going to the west. Okay, and then so now if we wanted to do the other one, because we're supposed to do for both, I'm wondering if it's necessary, but well, you know, might as well. If you don't want it, then you can just skip ahead. So that's for the final, for the first ball. The second ball is VF2 equals M2 minus M1. Notice the difference, M1 minus M2. This one is M2 minus M1 over M1 plus M2 times VI of the second ball, so it's times 0, so we don't even need to do that any further, times plus 2M1, the other one was 2M2, 2M1 over M1 plus M2. Can you guys hear that honking? I can. VI1. Man, this reminds me of remote learning. Well, this is exactly what this is. I don't want to do it like this. Speaking into a camera. Equals, that's 0 plus M1 was 0.08, so it's 0.16, 0.16. M1 plus M2 is 0.14. VI1 was negative 7. Oh, hang on, M2 minus M1. Oh, I added M2 minus M1, so this is actually negative 0.02. So negative times negative, we're going to get a positive out of this. So 0.02 times 7 divided by 0.14. That's a 1 as well? I don't think it was. Oh my goodness. No, I had it right. I got distracted. I was thinking M2 minus M1, that's where this came from. It was 0.16. Sorry. 0.16 times 7 equals this, divided by 0.14 is 8. 8 meters per second, sorry, 8.0 meters per second. And this one is negative as well, so that is going to the west. Can you dig it? Sorry about that mistake there. Let's do second practice. I don't like just talking by myself. So let's practice number 2 on page 247. A 1.2 kilogram glider, M1 equals 1.2. Moving at 3 meters per second to the right, V1I equals 3. Elastic head-on collision with a glider of equal mass, M2 equals 1.2. v2i equals, but it is going 3 to the left. Okay, so these are completely opposite, opposing. The collision is cushioned by a spring whose spring constant, 6 times 10 to the 4, which is 1, 2, 3, 4, so 60,000 newtons per meter. Determine the compression in the spring when the second glider is moving at 1.5 meters per second right. Okay, so for part A, V2F equals 1.5. Okay, it was going left, now it's going right. So in this case, we have two unknowns. If we look at that original equation, I don't want to write it out right now because we'll have to do it after. But the like 1/2 mv squared plus 1/2 m2v squared, etc., 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 etc. We'd have two unknowns because we don't know how fast the first ball is going, or glider, whatever it is. Plus, we don't know how much the spring is compressed. And that's what it wants us to find, is the spring compression. So what we need to find first is the final velocity of the first object. Now remember, we can use the momentum v1i plus m2 v2i, conservation of momentum equation, m1 v2i plus m2 v2f. This is an f. Initial, final. So we can plug in here to see, because conservation of momentum happens. So 1.2 times 3 plus 1.2 times negative 3. It's going to equal 0. 1.2 V2, well, that's supposed to be V1, sorry, V1. V1F plus M2, which is 1.2 times, we know it's going 1.5. So we're solving for this. So these cancel, that's 0. 1.2 times 1.5. 1.2 times 1.5 is 1.8. So it's negative 1.8 equals 1.2 V1F. So we divide both sides by 1.2. V1F is going to be 1.8 divided by 1.2. 1.5. Works out anyway. So it's negative 1.5. And that is going to the left, right? Because it's negative 1.5. So now that we know what the V1F is, we can plug it into our big nasty spring equation. Let me find it. So the equation is 1/2 m1 v1i, v squared, it's kinetic energy, plus 1/2 m2 v2i squared equals 1/2, I just realized I'm looking at the wrong equation, m1 v1f squared plus 1/2 m2 v2f squared plus 1/2 kx squared. That's fun, hey? Look at all that writing. So notice there's a half in front of every single one. So we multiply everything by 2 and it's all gone. I don't know if this was caught on camera yesterday or recorded, but Gavin was saying, well, then why? If you're just going to drop them all, why are they there in the first place? Because taken on its own, this is kinetic energy. Taken on its own, this is potential spring energy. So we're just using what already occurs, putting them together. It just works out nicely that we can take all the halves away. You could, like, what I thought about doing is writing this out without the halves, but I want you to know that they are supposed to be there, and then you can get rid of them. M1, so 1.2, V1 is 3 squared plus M2 is 1.2 times negative 3 squared equals 1.2 times V1 is negative 1.5 squared plus 1.2 times 1.5 squared plus k, which is 60,000, x squared. Cool, cool, cool. Let's do some of these. So this is 3 squares 9. 9 times 1.2. 9 times 1.2 is 10.8. So that's 10.8. Plus this will be 10.8 as well, because 3 times 3 is 9. Negative times negative is positive, so that's 10.8. Equals 1.5 squared. I'm not doing the negative because squares cancel, so 1.5 squared equals that times 1.2. 3.375. Okay, I'm going to skip a step here. I'm going to double these, so just I'm adding them together, and then I'm going to subtract these. That's what I'm going to do in one step. So 2 times 10.8 equals 21.6 minus 3.375 minus 3.375, 14.85, 60,000 x squared, so it's 14.85 divided by, it's all on camera, 60,000, we take the root of that, that's going to equal x, divided by 60 equals that, and then the root of my answer, 0.0157, so that's 0.0157, which equals 0.016 meters, which is 1.6 centimeters. Is that the answer? Did I make any mistakes? No mistakes yet. Second question says calculate the maximum compression of the spring. So hopefully that makes sense. For part B, I'm going to keep this sheet. Part B, maximum compression of the spring. Now remember, we got a different formula for maximum compression, which was, okay, I'm not going to, I'll still write the halves and then take them out. 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 plus m2 vf squared plus 1/2 kx squared. Now, here's the thing. So we can cancel all these kind of halves. Sorry, what is this question asking? Maximum compression of the spring. At maximum compression, notice these two share a velocity. It's zero velocity. If you have two things coming towards each other, do I have something springy or squishy? This is going to look weird, but whatever. You have two things coming towards each other. As they come towards each other and the spring kind of collapses, it only gets so far. At where it gets so far, it stops. Everything stops. There's no velocity. It's zero because it's in all the way, and then they whoop, and they shoot away from each other. They press away from each other. For this to go this way and this to go this way, they stop. They'll go as far as they can, and then they go reverse direction. So there has to be a zero in there, and that's what we're doing right now. So dropping all the halves because we can. M1 is 1.2. V1I is 3 squared plus 1.2 times negative 3 squared equals, this is just going to be 0, plus K is 60,000 x squared. Who's texting me? Is it important? It's not. So this is 9 times 1.2, which is 10.8. We can multiply by 2 because there's 2 of these bad boys there, times 2. So that's 21.6. 21.6 divided by 60,000. Take the root of that. That equals x. 21.6 divided by 60, 1, 2, 3 equals that. I'm going to take the root of that. I don't need to hit my shift button. Root. My answer, 0.01897, which equals 0.019. meters, which equals 1.9 centimeters. Hopefully that makes sense, gentlemen. Let me know if you got questions.